So hello everyone, today we will be discussing a problem from the B.Math 2012. We will be discussing this particular problem. So I will show you a method on how to solve this particular problem for any number n. And it will be a visual method, so let's see how to solve this particular problem. So let's start our idea by a general discussion of a equation x square plus y square equal to a square. So geometrically, what does this mean? So from coordinate geometry, we know that this is the equation of a circle. So here it is. Here we draw a circle like this, and in this particular equation, the a represent the radius of this particular circle. This means if I draw an arrow from the origin to any point on the circle, its length will be a. So the solution of this particular equation means how many lattice points that does the circle hit in this coordinate plane. So here for this particular drawing, you see that there are none. So there are no solutions of this particular equation. Let's take an example. So let's take this particular equation, which is x square plus y square equals to 3. So we draw a circle whose radius is square root of 3, as you can see here. Now as you can see, it does not go through any lattice points in this Cartesian plane. So there means there are no solutions for integer x and y. Now let's take another example, this particular equation. So we draw a circle whose radius is 3. So let's draw it here. In this case, you can clearly see that there are 4 lattice points which this circle hits. So this means there are 4 solutions for this particular equation, integer solutions, and these solutions are shown by red dots. So this is the idea for this particular solution of the problem. So let's now see a systematic way to solve this particular problem. So now let's once again write down our equation, and notice that the right hand side of the equation can be factored out using the idea of complex numbers like shown here. Now what does this mean? This means that if a number can be written as the sum of 2 squares, then I can factor it out using complex numbers. And recall that in our Cartesian plane, if I want to represent a particular point on this particular plane, any particular point, then I do it using a distance from the y-axis, which is represented by x, the yellow line, and the vertical line, which represent the y. And for that particular point, our coordinate is 2, 1, and I can represent that using a complex number 2 plus I. So this means that using the same idea, every point on this Cartesian plane can be represented using a complex number x plus I, y. Now, there is a specific type of these complex numbers. So let me define them. So if there is a complex number whose real and imaginary both coordinates are integers, then we call them Gaussian integers. So this means that in our coordinate system, each of the vertices or each of the lattice points are actually Gaussian integers. As you can see in this case, each of these yellow points represent a Gaussian integer. So now I can translate my original problem using the Gaussian integers. So if I draw a circle and suppose it passes through some points, then the equation which represents this particular circle has some solution. And the number of solution is actually the number of Gaussian integers on the particular circle. I hope this particular idea is clear. Now we need some more ideas to solve this particular problem. So once again, notice our main equation. So in this equation, I am factoring a number n using some complex numbers. So how can I tell if it is possible or not? To do that, let me first define another term which are called Gaussian primes. So if I have a Gaussian integer which cannot be factorized any further, then we call them Gaussian primes. Like 5 plus 3i can be factored out in this term. So it is not a Gaussian prime, but those two numbers cannot be further factorized. So they are Gaussian primes. For a number 5, which is an ordinary prime, I can factor it out in Gaussian primes. Okay. Now if I see the number 3, that this particular number cannot be factored even in Gaussian integers, the set of complex number. That means that 3 is actually a Gaussian prime. So how can I know that if a number is Gaussian prime or not? So here, to find if a number is Gaussian prime or not, I will use the Fermat's 2+ theorem. It says that if I have a prime number n and it has a form of 4k plus 1, then it can be written as x² plus y². So this means that any number which is of the form 4k plus 1, that is prime numbers, can be factored out. And the prime numbers of 4k plus 3 are actually Gaussian primes. So this means that if I have a prime number n of the form 4k plus 3, then x² plus y² equals to n does not have any solution. So I hope this is clear. So now let's see how to extend this particular idea for any general number n, which can be composite or which can be prime. So now let's see the non-uniqueness of a factorization. So let's suppose we take this particular number. Now this particular prime factorization is unique if I take just the positive integers. But if I conclude all the number lines, then I can multiply sum of it with -1 and the neat result will be exactly the same like before. So let's take another example to see this. So now here in this case too, I can multiply the 3 and 5 with -1 and the result will be exactly the same. And I can also multiply -1 with the 2 and -1 with the 5 and the result will be exactly the same. So this means if I include negative numbers, then the prime factorization is not perfectly unique. It is almost unique. And the reason is the existence of two unities, 1 and -1. So is there some similar thing in Gaussian factorization? Yes, indeed. So I have taken this particular number and now I can multiply the first one with I and the second one with -I. And I can multiply the other two with -1s and I will get the exact same number. So here too the factorization is not perfectly unique. It is almost unique and the reason is the 4 unities. So that means when I am finding the number of factorization, I can just find the factorization for the one unity and just multiply it by 4 to find the number of factorization. And I will be using this particular method. So I hope you have understood this particular point, that the factorization is not always unique. It is almost unique if you does not include the other numbers, you just include 1, then it is perfectly unique, but not in general case. So now let's see how to find the number of solutions for a number n which is of the form 4k plus 1. So let's start by this particular equation where n is 5. So first what I have to do, I have to factor the 5 in the set of complex numbers. So I can write it like this and you can see it is giving me a conjugate pair. Now what I have to do, I have to arrange them in a column here. This step seems trivial for this particular case, but it is one important step. Now as you can see that each of these 2 points has a magnitude of square root of 5 as can be verified by this particular equation. So this means these two numbers are actually on a circle whose radius is square root of 5, which is actually represented by our equation. So let's draw the coordinate plane and draw the circle. So on this circle, the 2 points are situated. Let's mark out those 2 points. So these two. So these two are my solutions as shown by the figure. Now what I can do, I can multiply the first one with I, that means rotate it counterclockwise by 90 degree as shown, and I can multiply the second one with -I, that is rotate it 90 degree in the clockwise direction, and it will generate 2 more solutions here. Now again I can multiply the first one with -1, which is equivalent to 180 degree rotation, and I can do the same for the second one. Now I can multiply the first one with -I and the second one with I, and it will again generate 2 more solutions because the factorization is not unique due to the 4 unities. So the total number of solutions is 8 as suggested by the figure, and in calculation I can get it by doing 4 times 2, which is equals to 8. So for this particular case, so for any number n of form 4k plus 1, there are only 8 solutions. So now let's increase the power by 1. So now I will be taking 5 square equals to 25. So in this case again, so for doing this case, let me first change the grid size so I can plot the circle. So first let's do that, and now let's follow the exact steps. Let's now factorize 25. As there are 2 5s inside it, I will get 4 complex numbers. As you can see here, and each of them, these are conjugate pairs. Now what I have to do, I have to arrange them in columns. So I will take 2 of 2 plus I in one column and the other 2 minus I in second column, as shown. Now each of these has a magnitude of square root of 5, but I need the magnitude of 5. So I can multiply column wise these two terms. So I will get something like this. Now notice that these two numbers have actually the magnitude of 5. So they are on the circle of radius 5. So let's mark these 2 points out here, as you can see the yellow points. Now I can again rearrange them in a little bit different way. So I can take the conjugate pair in one column, and in second column I can do the same like shown here. And in this case, if I multiply to generate the magnitude of 5, I will get the exact 5, the integer 5, as shown here. So this is also a solution which represents the 5, 0 point, as shown in the figure, this particular point. Now again, as there are 4 roots of unity, I can rotate the whole system by the multiple of 90 degrees and can generate all the solutions. Here, as you can see, it generates all the solutions, and it is equivalent to the fact that I have 3 numbers and I am multiplying it by 4, so there should be 12 solutions. So, and indeed I have 12 solutions. So now think about it. If I draw a unit circle, you can check it yourself, I will have 4 solutions, which is equivalent to the case of 5 to the power 0. So for a number 5 to the power 0, I have 4 times 1 solution, that is 4 solutions. For the case of n equals to 5 to the power 1, I have 8 solutions, which I can write it as 4 times 1 plus 1. For this particular case, I have 12 solutions, which I can write as 4 times 1 plus 1 plus 1. So for 5 to the power n, I can write it as 4 times the summation of n plus 1 ones. And it is somewhat a formula, a general formula, and keep this to your back of your mind. And now let's find how to solve this particular problem, the number of solutions for a number which is composite. So now let's suppose n is a composite number with a factor, single factor of 4k plus 3 prime, like this, 75. So there is a single factor of 3. So let me first draw the Cartesian plane and let's draw the circle. Now let's factor this 75 in the set of complex numbers. So you can see that I am getting something like this, as shown in the screen. So as 3 is a Gaussian prime, I can't factor it any further. So now let's arrange all of this in a column. So if I do so, then you will see something like this. Now no matter what I do, I can never arrange the 3 equally for the 2 columns. What does this mean? This means I am screwed. I will never get numbers which has a magnitude of square root of 75. That means that any combination of these numbers will never be on the circle. That means that the equation does not have any solution. And if you say that there are few solutions, let me zoom it out for you, and you will see that indeed there are no solutions all over the circle. That is, no Gaussian integers are on the circle. So what does this mean? The conclusion from this is that if n is a number and inside n there is a odd number of 4k plus 3 primes, then the equation x square plus y square equals to n does not have any solutions. Now let's see what happens if I increase the power of 3. So in this case, as you can see, if we have a even number of 3, we can distribute them symmetrically between 2 columns. So because of that, we can generate three distinct numbers which have a magnitude of square root of 225, that is 15. So we will get three numbers on the circle, that is Gaussian integers, and we can rotate them 90 degrees and we will generate other solutions. Now here the most important thing is we are exactly getting the same number of solutions which we have gotten for the case of 5 square. So this means that if there are even number of 4k plus 3 primes, then the solution does not depend upon them. The solution is exactly same for the case when they are not there in the equation. Okay, so now let's see the conclusions. So that means that for the number of solutions for a number 5 square times 3 to the power 0 is 4 times 3 times 1. And for the second case, we see that we cannot distribute the single 3, so it was 0. So I can multiply it 1 minus 1. So for the next case, I am getting exactly 12 solutions. So I can write 1 minus 1 plus 1. So if there are n power of 3, then we will get a oscillating series of 1 plus 1 minus 1 plus 1 minus 1. So from this, the conclusion is that the contribution of the power of primes of the form 4k plus 3 is actually an oscillating series of 1. So I hope this particular idea is clear. So now let's see that what happens when there is a factor of 2. Because 2 is actually a very special prime in this particular case, and we will see why. So now let's see the case for the 2 to the power n factors. So what do I mean by this is now the n number has a factor which is a multiple of 2. Like this particular example, here there is a 2 and there is a 5. So first we factorize this particular number in complex set like this. So the first 2 comes from the 2 and the second last 2 come from 5. Now I can rearrange them in a column like this, and then what I can do, I can multiply with respect to each columns to generate a number which has a magnitude of square root of 10, so that it situates on a circle like this. So now let's draw our coordinate plane and the circle so that we can mark out these 2 points. So now let's mark out these 2 points. So as you can see, I can represent them by a yellow points, these 2. Now what I can do, I can again rearrange them in a different sort of manner where I can swap 2 positions. So let's make another box here. Now in this case too, I can multiply with respect to 2 columns to generate a number whose magnitude is square root of 10 like before, and I will get these 2. And now again let's mark these 2 out in our graph, and let's choose a different color for the arrows. Now think about it, notice one thing, that the 2 pairs which I have gotten from the 2 are 90 degree out of phase from one another, these 2 numbers. So that means if I multiply 1 by I, then it generates another one. This means that it is already counting the fact that I will be multiplying by I at the end of the method. So this means that I only need to multiply these 2 vectors by minus 1 to generate all my solutions. So this particular method is a little bit different. So to make this particular method like the previous case, I have to do something different. So what I can do is that I can neglect the second box completely and just consider the first one. If I do so, then I am neglecting the fact that there is a row which is counting the multiplication of I, and then I will only have 2 vectors or 2 solutions, and I can multiply it by 4 unities to generate all my solutions. So why I can do that? You have to understand that I am able to do this because the 2 complex numbers which I am getting from the number 2 are counting the I, the rotation by 90 degrees. So if I omit another row, then I will get exactly the solutions by just multiplying by 4. So what does this means? This means that the factor of 2 does not help or hurt. So this means that any power of 2 does not increase or decrease the number of solutions. I hope this particular idea is clear. So this means that when there was 2 to the power of 0, at that time I have 8 solutions. Similarly, if I have a number of 2 to the power 1, that is for this particular case n equals to 10, I also have 8 solutions. So I can write the factor of 1 plus 0. So if I increase the number of 2 again by 1, then also I will have 8 solutions. So I can write 1 plus 0 plus 0. So you can see from here that 2 actually does not increase the count. So now let's go to the end game. So we are in end game now. So let's take a general number to see how to apply that particular idea. So I have taken this particular number and factorized it. So now let's see that the first number is a 2 and it does not hurt or help. So the contribution of 2 in the solution is 1, exactly 1, or any power of 2 will do the same. So it is 1. Now for the second one, you can see that 3 is a number which is of 4k plus 3 form and it has a power of 2. So it will give a oscillating series of 1 with 3 ones. So 1 minus 1 plus 1. Now the last number is of the form 4k plus 1 prime and its power is 3. So now we will get a sum of 4 ones. So 3 plus 1, 4, so 4 ones. Now, so from here I can say that the number of solutions of x square plus y square equals to 2250 is 4 times the contribution of all of these numbers, which is equals to 16, and indeed it is 16. You can just verify it by writing a code or by drawing a big circle. So now let's see how to solve our real original problem. So this one, so I have factored it out. Now you can see that there is 2, 3, and so I can distribute them equally, or there is 2, 3, so I will get an oscillating series of 1 whose contribution will be exactly 1. Now for the second number, it is a number of the form 4k plus 3 and its power is 1. So its contribution will make it 0. So this means that there are no solutions of our particular equation. So you can actually generalize the formula much more, but I think this particular method is much more easier. So this is all for today. I hope you have understood this particular idea.